tension into the y and into the x direction, as we have done before. So this is going to be the y component, this is the x component. So this y component equals t cosine theta, and the x component equals t sine theta. And now I'm going to write down the differential equations of motion, first in the x direction. Second, Newton's second law. Ma equals, this is the only force in the x direction. It's a restoring force, just like with the spring. I therefore have to give it a minus sign. So equals minus t times the sine of theta. T itself could easily be a function of theta. So I have to allow for that. The sine of theta equals x, if it's here at position x, divided by L. And so I can write for this minus t, which may be a function of theta, times x divided by L. That is my differential equation in the x direction. And I prefer always for this a to write down x double dot. Now the y direction. In the y direction, I have m y double dot equals. This is my plus direction, so I have t cosine theta minus mg. This is equation 1, and this is equation 2. And so now we have to solve two coupled differential equations, which is a hopeless task. It looks like a zoo, and it is a zoo. And now we're going to make some approximations. And the approximations that we will make, which we will often see in physics when something oscillates, is what we call the small angle approximations. Small angle. We will not allow theta to become too large. I'll be quantitative. What I mean by too large. When theta, which is in radians, equals much, much less than 1, we call that a small angle. If that's the case, the cosine of theta is very close to 1. You will say, well, how close to 1? Okay, 5 degrees. The cosine is 0.996. That's close to 1. 10 degrees. The cosine is 0.985. That's only 1.5% different from 1. So even at 10 degrees, you're doing extremely well. So this is consequence number 1 of the small angle approximation. But there is a second consequence of the small angle approximation. Look at the excursion that this object made from equilibrium in x direction. That's this big. Look at the excursion it makes in the y direction. It's this small. It's way smaller than the excursion in the x direction, provided that your angle is small. I'll give you an example. At 5 degrees, this excursion is only 4% of this excursion. At 10 degrees, this excursion is only 9% of this excursion. And since the excursion in the y direction is so much smaller than in the x direction, we say that the acceleration in the y direction can be approximated to be roughly 0. There is almost no acceleration in the y direction. With these two conclusions, which follow from the small angle approximation, I go back to my equation number 2. And I find that 0 equals t, which could be a function of theta. The cosine of theta is 1 minus mg. So I find that t equals mg. Notice it's no longer even a function of theta. So I simply have in my small angle approximation that I can make t the same as mg. It's approximately, but I still put an equal sign there. I substitute this back in my equation number 1. And so now I get that m times x double dot, and I'll bring this on the other side, plus t is now mg, mg times x divided by L equals 0. And now comes the wonderful result, x double dot plus g over L times x equals 0. And this is such a beautiful result that it almost makes me cry. This is a simple harmonic oscillation. This equation looks like a carbon copy of the one that we have there. Here we have k over m, and there we have g over L. That's all. Other than that, there is no difference. So you can write down immediately the solution to this differential equation. X will be some amplitude times the cosine of omega t plus phi, just as we had before, and omega will now be the square root of g over L, and so the period of the pendulum will be 2 pi times the square root of L over g. Just falls into our lap, because we did all the work. I want you to realize that these results for a pendulum have their restrictions. Small angles, and we discussed quantitatively how small you would like to allow, and also the mass has to be exclusively in here and not in the string. We call that a massless string. To give you some rough idea of what these periods will be, substitute for L 1 meter. And you take for G 9.8, you take the square root, and you multiply by 2 pi, and what you find is that the period is about 2 seconds. So, a pendulum 1 meter long has a period of about 2 seconds. 1, 2, 3, 4, 5, 6. So to go from here to here is about 1 second. If I make it 4 times shorter, L 4 times shorter, the square root of 4 is 2, then the period is changing. 4 times shorter, the period must be 2 times shorter. We'll make roughly 25 centimeters. I'm not trying to be very quantitative here. Now the whole period must be about 1 second. 1, 2, 3, 4, 5, 6. So roughly 1 second. So you see that the period is extremely sensitive to the length of the string. I now want to compare with you the results that we have for the spring with the results that we have from the pendulum to give you some further insight. We have the string and we have the pendulum. And I'm only going to look at the period t, which here is 2 pi divided by the square root of m over k, and here is 2 pi times the square root of L over g. If I look here, there is a mass in here. If I look here, it's independent of the mass. Why is there a mass in here? That is very easy to see. If I take a spring and I extend the spring over a certain distance, then there is a certain force that I feel. That force is independent of the mass that I put at the end of the spring. The spring doesn't know what the mass is you're going to put on. All it knows is I am too long and I want to go back to equilibrium. That force is a fixed force. If I double the mass, that fixed force will give on double the mass half the acceleration. If the acceleration goes down, the period of oscillation goes up. It's very clear. So you can immediately see that with a spring, the mass must enter into the period. Now go to the pendulum. If I double the mass of my bob at the end of a pendulum, then the vertical component of the tension will also double. That means this restoring force, which is proportional with the tension, will also double. So now the restoring force doubles, and the mass doubles, the acceleration remains the same, the period remains the same. So you can simply argue that there should be no mass in here, and there isn't. How about this k? If k is high, then a spring is stiff. What does that mean, a stiff spring? It means that if I give it a small extension, that the spring force is huge. If I have a huge spring force, the acceleration on a given mass will be high. If I have a high acceleration, the period will be short. And that's exactly what you see. If k is high, the period will be short. G. Imagine that you have a pendulum in outer space, that there's no gravity, nothing.